more interested here in making sure that you have a good grasp of the material and you know how to do things rather than judge you, right? Okay? My interest is making sure that you come out of this class with good understanding of the topic. Regarding the midterm, there were some of you that did not get their papers, so if you come forward here, I can give you a paper if you weren't here last time. Which number is this? This one. Now, I'm just making sure. Yeah. It's your paper, this one. I asked my helper to post the video from Monday so you can watch at least the last 10 minutes or so and you know what's going on with the midterm. Maybe the first few minutes and the last few minutes, so you get the instruction on how to resubmit that. Okay, there are two more people.
So you said if you got a part completely correct, you don't have to read it again, right?
Well, if I do appreciate if you redo the whole thing with neat presentation, okay? Because I've seen lots of scribbling, and I like to see the Smith charts well labeled, okay? Like this is Y1, this is Z1, this is how much distance we move, all that kind of thing. Doing all these arrows and coming up with a final answer is not a good presentation. It doesn't reveal the good understanding of the topic. So, unless you are, it would be a good idea to just redo the whole thing, right? If you've done it right the first time, it shouldn't take you more than a few minutes. And like I mentioned, some were very inefficient in the presentation. I've seen things that can be done in 2 or 3 lines that people took a page or 2 or even 3 to present. So, try to grasp the concept and get to the point right away rather than doing 100,000 things. That always shows how well you understand things, how much you are in command, instead of trial and error, walking all over the place. Okay, I went over my notes, the one that I haven't completed yet. These are my old notes. By the way, these old notes are already on Scholar as well, so you can look at the old notes if you wish. The notation is not identical, but close. And there are a few things that I have not covered, so I'd like to go over those with you today. Last lecture I tried to cover a few of the missing things, but I discovered that I have more missing things than I thought. One important one is the group velocity, right? We talked about the phase velocity, and we discovered that the phase velocity can be greater than the speed of light, and we mentioned that there's nothing wrong with that because the phase velocity does not indicate any motion or any energy flow or anything that can conflict in this regard. And by the way, I have a few things here, show and tell. Maybe I should send them around while I'm doing the lecture, so let me get them out. Because we're going to cover some of those components today. weights as I was coming from Whitmore Hall. This one here, this little tiny guy, is the one that I mentioned to you last time, having the mode filter built into it, right? If you can see inside, basically, as you can see, the waveguide is designed into a split, and they assemble the thing while putting those vertical shorts in. So you'll be able to see that. Hence, I can send this around one by one. This one is a straight section or waveguide, right? And the thing is, you can see some details in the design of the flange here, right? Some of them you will have straight flange, and some others you'll have some of these stems. And I'd like to explain to you what these things are for. In fact, this particular one have two sets of circles. The outer one basically is a place where you put some rubber gasket to seal the thing from dust and moisture and all that. But the inner one is very much electromagnetic, right? The inner one basically, if you are putting the waveguide together like that, and you rely on the metal touching the metal here and causing a short, you stand a chance of irregularities in the surface and energy leakage out there. And obviously leakage means radiation, safety, also impedance mismatches, you know, it can be both ways. So the design is, instead of relying on these touching each other and causing a short, why not rely on the real short to cause the short itself? Okay? Now, if you connect that to a flat one, let's say, all right, the energy leaks from here, we'll see a short circuit here, and if the distance from here to there is lambda by 2, this short circuit reflects the short circuit here, right? Okay? We know that a short circuit lambda by 2 away will reflect a short circuit. So basically, you can get a better short performance across here than just relying on the contacts there, right? This one is same thing but a smaller guide for higher frequency range. A flexible one, right? Sometimes you need to adjust, connect two guides to each other, and they may not be the right position with respect to each other, so they flex this way, and there are some others, you can flex it this way too. I don't know if you can twist that. You can't twist that much, but some of them you may be able to twist, but they also make twists. So I'm going to send these together. In terms of bends and twists, there are two types of bends. There is a bend in the electric field plane, and there is a bend in the magnetic field plane. I don't have a bend in magnetic field plane. Well, you can picture this one as one, right? If you can go this way, right? If you go this way, this bend here is in the H field plane. So if the bend is in the broad dimension or the bend is in the narrow dimension, right? These are bends. And I'm going to show you here the field distribution in both cases. And they make those bends sometimes the whole 90 degrees or 45 degrees or whatever degrees you need. This one here has an adjustable shutter, all right, which you may move up and down. The thing is broke, so it doesn't move, right? But you can see. So you can actually introduce some partial, let's say, iris kind of thing in the field, and that has its own application. There are also the hybrid T, all right? This one here has two bends, all right? I'm sorry, two T's. One T in the E-plane, as you can see, here's a T in the E-plane. The E-plane is a broader dimension. And here's a T in the H-plane, and both of them are combined in what we call a hybrid T, right? And the hybrid T is again, well, the T and the hybrid T are both mismatched. One of the homework assignments that you have in homework 3, you will see that your junction there is mismatched. Now, this one here is a mesh termination actually. This one here has some resistive tapered core inside, all right? So it absorbs the energy over distance and eventually causes a full match to the impedance there. So it absorbs the energy and sends some current back. They are just connected to each other, so we'll just leave them together here. This one is another T, as you can see, has an H-plane T and an E-plane T, causing what we call a hybrid T, except it has some magic things inside, all right? So actually they call it the magic T. And the reason calling it magic is it's done by trial and error. People that know this kind of stuff design these metal inserts that causes matching, causes impedance matching. They're basically reactances added inside, right? And they call that black art or black magic because there was very little that you can write in equations, and a lot that you can do is just experience. Now these two are adapters, coax adapters, waveguides, right? And there are two types here. One of them is electric field adapter, where you have an antenna probe that is sitting there inside the guide like this, that eventually causes the electric field to eventually propagate. And there is a magnetic field one, which is actually a short here, and relies on the current here to cause magnetic field that will launch your T10 mode, right? So the magnetic coupling and the electric coupling, both coming from an N-type connector. There's another bend that's not exactly 90 degrees, I guess. We have the 90 degree one, this is this one here is a coupler between a rectangular and a circular guide, right? And the circular guide actually also have a mode filter inside. So, very interesting situation. Finally, the directional coupler. We'll talk about directional couplers, right? We showed two lines on top of each other with few holes that are sitting in the right place here, okay? Except to distinguish them from each other, they make one of them move away from the other one, right? So this will be the main one, and this one here will be the detection one. Now, can we see the holes? If you look inside carefully, you can see the holes, right? You just have to get the right amount of light in there. They are actually slots rather than circular holes. Last but not least, that's a piece of guide with a cavity resonator sitting on top. And the cavity resonator is calibrated in resonance frequencies. So you put that on your waveguide and you monitor your signal flowing through and you look for a resonance, right? And you tweak that until the resonance happens, and you read the frequency right there, so you can read your frequency. We used to have experiments in the laboratory using these kind of things. I guess now we shrunk all the experiments to one that eventually Kareem is going to do for you, and it's going to be the slotted guide where you monitor the standing waves over a waveguide. Oh, vacuum tube. Did you ever see one of those? No. When I started my hobby of playing with electronics, that was it. And that came into two different types, shielded and unshielded. All right? And when this lights up, you can see the filament bright, and you can tell, and it gets hot, real hot. These things get real hot. Eventually, we'll talk about the klystron and the magnetron, which are still vacuum tubes, traveling wave tubes, vacuum tubes that are still in use until today. These are typically used in high power things, radar in particular. I want to show, obviously, if you sit down and do field analysis to any of these devices, you are asking for, I hate to call it trouble, right? It's too much analytical work, right? And besides, you don't have the math really to be able to write the field equations for these kind of transitions. Even a simple one, like a T, all right? If you try to write the equations for that, it's going to be very complicated. That's your E-plane T, as we call it, and the H-plane T would be like this. So if we have those in a system, and we'd like to analyze the system, what do we do? All right? What we do is resort to the S parameters. We develop the scattering parameters of these devices and use them instead of working out the field equations. Okay? So basically, you would think that you have a line here, another line going there, so you can just approximate that to two transmission lines like this. So it would be like the stub problem that you worked on before. Okay? That's an approximation. That's not really an exact thing. So you would picture that if your electric field goes in here, for example, that electric field is going to propagate inside the guide until it gets to here, and eventually it's going to split itself and propagate both ways. So if I were to write the scattering parameters for that, and I'm doing here an approximate thing, I'm not going to do you the exact equations because we are not interested in the full details here, we're interested in the concept itself. So if you call this port 1, port 2, port 3, all right? Typically, well, that's okay, I already called them that way. So what happens here is this impedance and that impedance in parallel with that impedance, all right? So you get eta, z, all right? Eta and eta, that's 8 over 2 connected to eta, so you have eta connected to 8 over 2. So obviously you have an S11. And that S11 is what? 1/2 minus 1 divided by 1/2 plus 1. That is minus 1/3.